Okay, the next example will be question 5. So, again, very fortunate we are given the relative, or rather the molecular formula of the final products that we are supposed to find out. C11H12O3, if you do a quick calculation here, you will get a degree of unsaturation of 6. Okay, so again, we will just follow the same protocol. We just go straight perhaps to the 1H NMR, check out the aromatic protons. We have 5 aromatic protons, so probably is also a mono substituted phenyl ring. So you have a 4 degree of unsaturation due to the presence of a phenyl ring. You have 2 more, which might make it look a little bit harder this time round, because having 2 could be 2 rings, 1 triple bond, or two double bonds, or 1 ring, 1 double bond. So you can have quite a number of combination. But if we do some preliminary analysis, you realize a very interesting phenomenon. You'll notice that over at close to 1700, you have a peak slightly above, you have a peak slightly below. So this actually throws some lights that maybe I'm going to have 2 different types of C double bond O stretched. Okay, so maybe we can just KIV this for a while. We don't really need to conclude. Remember that whenever we do structural elucidation, we need not be correct at the beginning. Okay, we can be wrong, or we can make some postulates. Okay, so there isn't a need for you to be right every time. So again, just draw a line above 3000. So you have some sp2ch stretch, some sp3, and maybe might I mean, it's not so clear, but maybe you have a aldehydic CH stretch as well. So another aldehyde group in the making. So again here, NMR about between 9 to 10. Okay, very characteristic of aldehydic protons. And this is a singlet, which means the aldehydic group is bonded to a carbon without any protons, or bonded to a group without any protons. Okay, the NMR is really neat here. So basically 3 likely to be methyl groups, singlets. One is slightly above 3.5, the other one is about 1.75. So from here we can probably guess that this particular uh, methyl group, right, is likely to be bonded to oxygen. I can straight away conclude oxygen here, because normally if the methyl group is bonded to a nitrogen, it will be slightly below 3, or just slightly above 3. Okay, if it's bonded to oxygen, methyl group, very characteristic singlet, usually it will hit close to 3.7. Okay, so this is something that you can have in mind lah. Okay, when you are actually doing the structural elucidations. Okay, so well, if you have a CH3 bonded to a oxygen, okay, and at the same time you have an aldehyde, and at the same time you have an ester, or rather a carbonyl group. So if you put the 2 things together, probably you expect the carbonyl groups to be one due to an aldehyde, and then maybe due to another one due to an ester. Okay, so with this coming into the picture, and perhaps looking at the structure of A, it seems that the phenyl ring remains probably untouched, and then there is likely to be a quaternary carbon. Okay, so let's just try to piece out all the information, and then we'll see how we can move from here. So okay, so we have let's have an aldehyde group. Okay, and then perhaps bonded to a carbon, and then this carbon in that sense is likely to be bonded to a phenyl ring. Okay, and then maybe bonded to another CH3. Okay, so remember, every step we take must kind of like make perfect sense. Okay, this is due to this is due to this. Okay, and then this phenyl ring is due to this. Okay, so we only have one more group to play around with. Okay, which is the ester. Okay, so in that case, can I then say that the ester is found here? Okay, we just do a quick count in the carbon. 1, 2, 3, 4, 5 plus 6 for the fan out ring, 11. Okay, so now everything, I hope it make perfect sense now. Okay, so this is here. Okay, so we have kind of like may have show you some of the thought process in actually tackling this particular problem. Probably this is a little bit easier because you have already done the earlier problem.